Because time is limited. Moving on, let's move to the next speaker. Our last speaker is Professor Bate Bate. Professor Bate Bate is a professor in Zhejiang University. He is an ISEG Council member. His research interests include permeable reactive barrier, microflood modeling, DEM modeling, unsaturated soils, band element, organic clay. Today, his topic, he changed his topic. His topic would be barrier performance, polymer modification, SIP monitoring, and velocity prediction. So, Professor Bate Bate, please.
Thank you, Professor Du. Can you hear me?
Sure, yeah.
Okay. Good morning, everyone. I'm honored to present here. Thank you, Professor Shi and the organization for giving me the opportunity. Today, my topic is barrier performance. I want to narrow down to three little things, namely polymer modification, the spectral induced polarization or SIP monitoring, and the shear wave velocity prediction. So this is my content. Now let's jump into the background. So there are massive solid wastes in China. In 2018 years alone, there are 6.1 billion tons of solid waste produced. So the composition as shown in the pie chart, industrial over half, 50%, and construction demolished waste, and also municipal solid waste, and others including approximately 1,000 tons of radioactive waste. So the existing solid waste are also massive, as there are around 60 billion tons in China by 2018, and occupy a large over 2 million hectare land. This figure below here shows mining waste rock dump sites in Jiangxi province in China. So you can see the pile, the height is over 300 meters and taking up a lot of land. And for those solid waste dump sites, barrier could be an effective way for the subsurface contaminants control. We go back to the mining site, the dump waste rock dump pile as shown in this figure. So if there is a precipitation or rainfall or snow, and there are free oxygen in the air, the pyrite will react with those ingredients and produce iron 3, and acid, as well as sulfuric ions. So on the surface, we can actually see, go to this side and see the rusty color showcasing the existence of iron, high concentration. And to eliminate or to contain those contaminants underground, barriers are very effective way. And in this figure, it's a kind of a new thing. We are proposing, or there are several cases already, engineering cases, on using the GCL, geosynthetic clay liner, and install them vertically, acting as a barrier. Those GCLs possesses very low hydraulic conductivity or permeability, and with the aim to retain the contaminated groundwater on the site. So there are increasing demands for barriers. First of all, the lifetime expectancy. We all know the municipal solid waste landfill, their lifetime may be 50 years or sometimes maybe even 100 years, but that's about it, and everything decomposed and harmless. However, for mining waste piles, approximately over 100 years are required. And if you look at industrial waste or hazardous waste, the lifetime expectancy are 300 years or more. And for radioactive waste storage facility, it's over 10,000 years. So those are quite high, very demanding for a barrier. And currently, the permeability of the current existing engineering barriers are as follows. So if we have the cement mixing pile, which are stiff and widely used, 10 to minus 8 meters per second. Soil bentonite wall, also widely used, has a permeability of 10 to minus 9. If you look at GCL, geosynthetic clay liner, 10 to minus 11 meter per second, but still this value sometimes may still fall short. So the current demands, as I summarized below, there are maybe 5 points. First, the low permeability. We are shooting at even lower permeability, as low as 10 to minus 12 or even lower. And also we require the good chemical compatibility against the acidic condition, as we see just a moment ago, the acid from the dump waste of mining operation. Also basic facility, basic condition, like in industrial waste or high salinity condition, which are occurred very often in those waste dump sites. And I did a little research on that. So I make a case one, polymer-modified bentonite barrier, which is very preliminary. And also the demand also requires the contaminants being retained by the barrier. If we're looking at a GCL or low permeable barrier, the barrier are required to have some absorption against the diffusion, because diffusion could be a major transportation mechanism rather than the advection. Or in some other case, for permeable reactive barrier or PRB, the contaminant dissolving or retaining capability are very much required. Also, the performance of a barrier, since it's underneath the ground and monitoring well can only give you scattered data at a limited space. So the performance monitoring are required, and that's a key issue. Also, how can we predict a barrier performance after maybe 100 years or even longer? So the performance prediction methods are also required. So from those three aspects, I want to continue my presentation. First, I'll go with the polymer-modified bentonite barrier, which I believe Professor Du and many of the audience are expert on this. So I just want to share some preliminary results from my group. And polymer modification in this study, shooting for a low permeability. So we use polymer PAA and CMC as the two candidate polymers. And the SEM shows that those polymers chains can link the bentonite particles and filling those voids and blocking those flow channels and forming 3D network structure. All this can reduce the permeability for the pore fluid, like water, to run through it. And if you look at the figures at the bottom right hand, you can see there are some exfoliation of bentonite particles after the PAA treatment. So we can see the pore size further reduced because of the exfoliation and subdivide the pore space available in the bentonite. So this way, the permeability are thought to be reduced further. So this is some SEM photo. So we have some preliminary results on the permeability. Maybe there are some, when I started, I also thought if I put more polymer loading dosage on the bentonite, the permeability would be lower. However, from our preliminary results, we find that at polymer dosage around 2% to 5%, the permeability can go as low as 4 or 5 times 10 to minus 12 meter per second. If I increase the dosage further to, let's say, 10%, there actually permeability increased. And so I observed from this limited study that the optimal polymer dosage could be around 2% to 5%. And if you look at the 5% results, the permeability can go 10 to minus 12, which meet our goal. And also, we can find that if we compare different polymers like a PAA versus CMC, the PAA modification use kind of a lower permeability than the CMC. And I also put in Fan Ridong and Shen Shengqiang, Professor Du's students, and also Hyperclay from the MDO, and some commercial polymer-modified bentonite for comparison. So we are reaching this order of magnitude. Next, the permeability is not everything, and the chemical compatibility is also important. Since we are dealing with the background of copper mine and how to deal with the acidic and heavy metal solutions and subsurface solutions, we are using the copper sulfuric salt, and we increase the concentration from 0 to 15 millimole per liter, and we find that the permeability increased by 2 orders of magnitude if we have a copper concentration of 15 millimole per liter. The field sample, water sample, give us a copper concentration somewhere around 0.5, 0.3 millimole per liter. So somewhere in where my mouse shows. So that means the permeability could be as low as less than 10 to minus 11, so which is still operationable. And we also compare with, if we look at the 0.01 mole per liter or 10 millimole per liter, so we are looking at 10 to minus 10 meter per second, which is regarded as a high salinity condition. So the permeability does increase by at least 1 order of magnitude. And if you look at the chart below, we find that 2 things. So both the polymers can reducing the permeability effectively. Either it's at salt content high salinity condition, pH over 3 acidic condition, or deionized water. Also, we find that the pH equal to 3 yields pretty much similar permeability than deionized water, showcasing the hydrogen concentration may play a similar role as the cations in the pore fluid. So that's our preliminary finding. And let's jump to the case 2. I want to monitor how the interaction between the contaminants and the barrier material. So I make a simple case of using the activated carbon AC, a typical permeable reactive barrier filling materials, and use it to remediate the lead 2. And we do a basic column test, and the breakthrough curve are shown as here. We also did biochar test, but I skipped the result of biochar. So there are some key issues like key factors, retardation factor, etc., listed in the table below. And what we are really trying to find out is how the contaminants, lead in this case, evolve the morphology and the size, the content evolve in the barrier, how we can measure it. So at the end of the breakthrough test, we did before and after the breakthrough test, we did the SEM test imaging as well as mercury intrusion test. And for the intact activated carbon, there are 2 major pores. One is around 100 micron, and the other is around 1 micron. And the size from the SEM image can be plotted as shown here. After the lead remediation, we find that there are precipitates, like needle-shaped precipitate with a size around 10 micron. And we took a single precipitate and used the high-resolution tunneling electron microscope. We find that the small single precipitate are actually the lead hydroxide crystal with matching the despacing, etc. So meanwhile, I monitored the whole breakthrough process with this so-called SIP monitoring, spectral induced polarization. Let me dial back a little bit and introduce how it works. So unlike the traditional electrical method, taking only the real part of the conductivity, in any particle, like a precipitate, as we saw just a moment ago, or clay like a bentonite, or even sand particle, or even calcite precipitate, the solid particle always surrounded by a cloud with cations around it, because the particle most of the time are negatively charged. And the cloud composed of primarily of cations or positive ions are commonly referred to as electrical diffuse layer. Those diffuse layers are like a marshmallow or cloud shape. If there are applied electrical field acting towards one direction, then the cloud will migrate. The migration actually is the migration of the cations, the physical migration. And if the electrical field reverses its direction, then the cloud will migrate to the other side. At either case, the center of the positive ions, cations, and the center of negative ions on the particle can form a dipole. So this essentially is store the energy of the electrical field. So the energy storage term is the imaginary part, which can give us very information of first how many of those dipoles are there. So the magnitude, the higher the magnitude of, we call it relaxation, if the applied field and the responsive field are completely out of phase, meaning their direction are completely opposite, the magnitude can give us an idea how many of those clouds are presented in the barrier. On the other hand, how quickly those cations can transport from one side to the other give us an idea how big the particle could be, because the larger the particle, the longer the distance the cation has to travel to reach the other end. So by those two simple mechanism, we can actually obtain two information. One is the size of the charging unit, which can be polarized and induced polarized. And also the other is the content, how many of those polarizable units are there. And all this measurement, I have to speed up, from the complex conductivity, which I would, one part is electrolyte, the other is the surface conductance, which can be further divided into real part, first two term, and the second part, imaginary term. So let me just show you the results. And this photo on the left-hand side give us an idea. As the lead breaking through the activated carbon, the imaginary conductivity, the magnitude actually increased monotonically. So that means more and more the charged unit are generated during the breakthrough process. The other feature we can find is that there are two peaks actually in this SIP response. And if we using the equation mentioned in the previous slide, right? So I can use simply the frequency of the peak and calculate what are the typical size of the polarizing unit, either it's a precipitate or it's a pore. So as we see from the SEM photo, we have this lead hydroxide crystal as shown here, and that from the SIP calculation, I can calculate that there are indeed this particle or crystal exist since the beginning of the test, and the size doesn't change. That's also makes sense because crystal doesn't really change as the concentration increase. And the other peak at a lower frequency, meaning the size are bigger. And comparing to the size of the AC activated carbon, we find that the size can only be the pore size, typical pore size within the activated carbon, meaning the lead, part of the lead are actually absorbed on the activated carbon pores, and they will go to the smaller pores over time as the size keep decrease. So that's second topic. The SIP can monitor the size and the content of the contaminant. And third, I want to present another case, how we can predict the behavior of a barrier by the previous mentioned technique. So the performance of a barrier facing many challenges as shown in this figure. First of all, if a barrier working for a longer time, there will be clogging and uneven flow. If there are chemical compatibility issues, there may be cracks, fissures, and causing the preferential flow, which fail the barrier. And also we have the contaminant retardation problem. If there is a breakthrough, the chemical side, it failed. And also on the mechanical side, since it's an engineering body, the thickness is somewhere between half meter to a few meters for the barrier. Even for GCL, it has a certain thickness, so it's an engineering barrier. It's subject to the horizontal stress underneath the ground. If the barrier becomes soft for some reason, like fissures, cracks, or shrinkage due to the compatibility issues, the barrier will cave in. So, and also we have the huge pile of waste rocks or some other municipal solid waste on top. So there will be a shear strength issue. So there is strength failure potential. So how and likely the contaminant will degrade the barrier performance. So how we can predict and see the barrier performance over maybe 10 or even more longer years. Here I want to have an example of stiffness, which can be evaluated by the shear wave velocity (Vs), and to do a test. First, I choose a very simple setup scenario: the enzyme-induced calcite precipitate, EICP, which only have an enzyme which is soluble, and also we produce the calcite, which is precipitate, and there are not too many complex issues. And we have two concentration. The first 6 per volume PV, I use a lower concentration, generate only small tiny amount of calcite precipitate. At the 7th to the 10th per volume, I use a much higher concentration, which generates a larger precipitate. I will show you in the next few slides. And this is the setup. This is the column, and that's my SIP unit. And those 4 parts are a band element, which is a traditional tool for measuring the shear wave velocity. I want to measure it and calculate to compare to the predicted one. So this is a solid column filled with sand treated by the EICP process, and there are a series of band element aligning. And for those of you, a band element is measured shooting a wave at 2 ends by the distance and the travel time from the received wave. I can determine the travel time and the length over time equal to the shear wave velocity. So it's a simple. Let me jump right to the results. So as time increases, the shear wave velocity will generally increase as shown. However, there are scattering in the data indicating in the soil column here, the calcite precipitate are not homogeneous. So there are 4 pair of band element results can be shown in here. However, we took average. There are certainly more calcite precipitate and more stiffness increment as shown here. I also want to quickly show how the size calculated from the SIP prediction. I skip the SIP signal, present only the precipitated calcite particle size. So for the first 6 PV, calcite size is only 0.1 millimeter, and at higher concentration, a 1 millimeter size of sand calcite cluster began to form, and also the calculated calcite content from SIP and also the measured from chemical method are shown here. It fit really well. So I know during the process, not just by the end of it, I know the content and the size of the precipitate. So then we implement those information into the discrete element method simulation. So for the first to 10th PV, the single calcite precipitate are always there. So as shown in the SEM EDS plot, they are at the contact. So I use a linear parallel bond contact model to represent the stiffness. Also, the volume calculation can be shown geometrically. I will not elaborate. And at the 7th to 10th pore volume, larger clusters of sand calcite are formed. So the size, remember, is 1.1 millimeter in that range. To simulate that, I bridging adjacent particles to simulate the cluster, and those bridging volume can also be calculated. So with those two different kind of precipitate pattern, I can proceed with my DEM simulation. I'll skip many steps for calibration, but essentially I use the real data to calibrate my simulation, the stiffness and damping ratio, etc. With some other techniques. The results are shown in this chart. So first, the average shear wave velocity results from my experiment earlier are shown in the solid line. And there are two stages. First stage, before the 7th pore volume, the calcite precipitate are primarily single point contact, so corresponding to an increment which fit very well with the experimental results. As the cluster began to show up, we can see the clusters can give a higher shear wave velocity, however, slightly lower slope of increment. And if we looking at the first PV, the precipitate is more like uniformly distributed. So the shear wave velocity propagation actually is like a big bang. So it's uniform from the center. And if we look at the 9th pore volume, where there are a lot of clusters formed, then we can see the preferential wave propagation paths are shown along the clusters, as shown in this. And at a higher calcite content, like 4%, which exceed my experimental value, you can see there are a whole lot of clusters. Then the shear wave velocity propagate preferentially along those clusters for their higher total stiffness. And if I use the existing results to predict what would happen at higher calcite content up to 10%, my test only end at 3.2%. And I can see two clear stages. First is there are more clusters spread over the soil column. And sometimes if the connectivity between those clusters are excellent, then the shear wave velocity will be higher. If there are gaps, shear wave velocity will be lower. However, this may not be much a difference if you have an even higher cluster concentration. So this is what we observe. And compared to some existing data, experimental data, our results show a good agreement. So summary, pretty much the topic. I will skip. I want to take the one last second to thank the funding agencies and my advisors, my mentors, my collaborators, and also my group members. They are really hardworking people. And thank you again for the organization giving me this opportunity. Appreciate it. Thank you.
Thank you, Professor Bate Bate. You put it in a very timely manner. We may have some time for one question. Do you have any question from the? Do you have some question from the audience? If no, do you have any question from the audience? Any question from the audience? So if no, if no, you can send an email to Professor Bate Bate for more discussion or communications. Thank you very much for all of the speakers, and thank you very much for all of the audience. Thank you. So I would like to close the session